So theoretically, what you guys have moved through so far is how we quantify some things, go roughly through chapter sequence. So how to quantify some measurements, that kind of stuff, and then you move into atomic theory, how do atoms build, and then we move into the trends in the periodic table so we can learn all that, and then we say, okay, now what happens when we start putting those atoms together? That's where we're building our molecules. Once we have an understanding of some of the bonding aspects and molecules, then you'll start running into chemical reactions and all that other fun stuff. When we look at an atom, what makes up an atom? Let's try that. How do we have an atom? What's that?
Charges.
Okay, so charges make atoms? Are there things that are charged? What are those things that are charged?
Electrons.
Okay. We've got protons, we've got neutrons, and we have electrons. If we look at an atom, what makes up the atom? That was stupid. We just answered that question.
All of them.
All of those things make up the atom. Where are those things located? They aren't located everywhere. We have a nucleus. Okay. In that internal nucleus, what do we have?
Protons and neutrons.
We have all of our protons and neutrons all densely packed into a nucleus. Then where do we have the electrons?
On the outside.
Somewhere on the outside. And this is where we get orbits, right? You probably saw or heard the analogy that you're looking at. If we made the nucleus a marble, the atom is a superdome, right? The size of the atom, the outer radius. So our radius is largely dictated based off of our electrons, not the nuclei. When we now move through into molecules, what we're concerned about is how those atoms communicate and talk to each other. Right? Well, at a first approximation, if someone's going to go through and now try and create a theory to explain how atoms bond, what particles do you think they're going to talk about interacting to make that bond?
The electrons.
The electrons. All of the electrons?
The outer.
The outermost electrons are the most likely to be referenced. Outermost doesn't sound fancy enough, so we invent a term, and that term is valence. Okay, so the valence is our highest energy electrons. We know our highest energy electrons because we've got electron configurations, right? Everybody's favorite? We've got, yeah, that's size appropriate, 2s2, 2p, 6, 3s, 2. And our energy level is located where in that electron configuration?
The last one.
Okay. The valence electrons are found in the last one, but I can very quickly make that not accurate. Those are valence electrons, but that's not all of them for this electron configuration. Okay.
The last full one.
That one's not full. And so I don't know if absolutely fair. That's absolutely fair to throw guesses out, and I would appreciate guesses. Once we have something to work with and talk about, we can move forward. If we don't have something to talk about and move forward with, we're just expecting an answer. Answers aren't useful because you need to know the content and where it's coming from, right? So if that's our electron configuration, right, there's certain pieces of information that are stored within it. One of them is the energy level. Where is the energy level specified in our electron configuration? And for the record, I don't know is a perfectly valid answer. Was that you saying I don't know?
Yeah.
Awesome. There we go. Okay. So where's the energy level specified? It's the number in front. That's the energy level. When we say 1s2, we're referencing the first energy level. Where's that found on the periodic table? That's the first row. Okay. Is it H? Not necessarily, because there's two elements in the first row. How would I know what element I was referring to? Officially, I wouldn't, because this is electron configuration, and our elements are defined by the number of what?
Number in front of it.
Nope.
Is that what you just said?
What defines the element?
Proton.
The protons. If this is electron configuration, I can change the electrons around and still have the exact same element because the protons aren't necessarily changing. So if we're now going to say, what are we referencing? What element are we referencing? We are making an assumption that there's an even balance of protons with it. that can be a very dodgy assumption. It's a valid one early on. That's what we talk about in chapter 4 and chapter 5. We're just saying it's a balance of protons and electrons, that they're the same. Not always true, right? But we start there as a starting point. So if we were now saying, I want to reference hydrogen, well, number one, I want to say the energy level. What energy level is it in? It's the first row. Guess what the first row is? First energy level, so I could call it 1. Ta-da! But now am I referring to hydrogen or am I referring to helium? That's a harder question. I need more information because both of them are in that system. Right? We could just say it's the first column in the first energy level. Right? That could become confusing, right? Why would that become confusing if I said it's the first energy level and it's the first column? Why is that confusing? If I wrote 1, 1. It looks like 11. Am I referring to the 11th energy level? No. Okay? So this is why we don't follow it with a number. We follow it with a letter to break up that meaning. That breakup in that meaning becomes more relevant as we move further down the periodic table. Right? But what we reference is anything in the first 2 columns we would call part of the first group. Doesn't quite work because there's a second column. I love the suggestion. It's an awesome idea. It just doesn't quite work for us. We call it part of the S block. So those first 2 columns are now saying our S block. So we could call this 1S. Which column in the S block are we located within? For hydrogen, we're in which column? The first. So we could call it 1S1. Now I'm saying hydrogen. This electron configuration doesn't say 1S1. It says 1S2, which means now I'd be referencing helium. Okay? That explains helium's 2 electrons. There's more things written here. Why are there more things written here? Because I need to look at elements beyond helium. Okay? So we've got our energy level, our orbital type, the column, which is ultimately referencing the number of electrons located there. Our periodic table stores that information. We didn't have to memorize it from chapter 4. We could just look at the periodic table and say how many columns were there, and we've got it. Kind of, sort of? Okay. So if we continue to build through 1S2, 2S2, okay, so there's 2s, 2p6, 3s2, 3p3. Your suggestion was our valence is the highest filled. That ain't filled because the p can fit 6. How do I know the p can fill 6? One awesome answer is there's 6 columns in the p block. Remember we called the first 2 S. This turns out to be the P. There's 6 columns within it. What's another valid answer? Earlier on, there was 2p6. Okay, it was already written in our notation. So our valence electrons isn't the one that's full. It isn't the furthest to the right. Our valence electrons are the highest energy. Where did we specify the energy level? The first number. So we can look furthest to the right, and we look at that, and we say, what's the number? 3. Is there another 3?
Yes.
Yes. Not that one. 3s2. So now when I want to refer to the valence electrons, I am referring to the highest energy. Those highest energy electrons, 3 and 3, for this particular electron configuration, the valence electrons are 3 is the energy level. The electrons are how many electrons are in those energy levels. That's the superscript. So the 3 guess is still fantastic. You're acknowledging the right thing, the energy level, but now we have to count the electrons. So valence is saying highest energy, now count the electrons located in that highest energy. Right? Kind of makes sense?
Yeah.
Do you guys like electron configurations?
No.
No. Do we want a different way to find the valence electrons?
No, it's pretty straightforward.
You just said you didn't like electron configurations, and you're like, no, yeah, let's keep that.
It makes sense, though. I don't like it, but it makes sense.
Is there easier
Is there an easier way? I like that option. Okay, let's figure out where this is located, right? Okay. So when we're looking at our electron configurations, the easiest thing for Chem 130 students to do is look at that last spot, find that last spot. We then make the assumption that we aren't being obnoxious and changing all of those into something wrong. Okay? If you have to move into Chem 151, you have to watch out for that. Chem 130, you probably don't. So just look at the last spot. So 3p3. What does that first 3 mean?
What is that word? Yeah.
Row, okay, it means what?
Which row it's in?
Our third row. Then it says P.
P is the last group.
Then it says 3 is a superscript.
Be the third one.
Now it's 3 over. So when I write that electron configuration, what am I referencing? Phosphorus. Okay? How many valence electrons do we say it had? 5. What? I mean, that says 15, but you all see that there's a 5 there, right? And then we just added a 10. Okay? That could just be random luck. It's just because it happened to be in that column. I just happened to select the perfect thing that worked, right? Okay? So let's switch it up to 3p. Let's make it 1. Aluminum.
Whoa.
That says 3, but that says 1.
Put them added together.
Wait, remember for our third energy level, it was all of those electrons within it. There's 2 sets, which means for aluminum, how many valence electrons do I have? 3. This electron configuration tells me that. It's also stored right on the top of the periodic table. That's like some genius level stuff. Somebody organized this so that we could think through it appropriately. That's neat. So we didn't have to deal with electron configurations. See, isn't it nice that you were like, yep, I don't like electron configurations, show me something else? There it is. Never works that way for the record, except this time. Okay? So when we're now going through to deal with the chemical bond concept, we've got our valence electrons. We want our highest energy electrons, right? And it's those electrons at that energy level. Well, how do I know what those are? I can do electron configurations, or I pick any element. Selenium. What are its valence electrons? God, do I really want to do 34 electrons for... Way to interrupt me. 6. We got 6 valence electrons. Sweet. Don't apologize for that. That's good. Okay, make sense? Okay. Chlorine. 7. Our valence electrons are stashed there, and we can build that out pretty quickly. That's neat. So we don't have to deal with those electron configurations. We have kind of a simpler approach that allows us to move through and find that. We good with that?
Yeah.
Cool. So those valence electrons are the ones that we start with saying are involved in bonding. Why do we pick our highest energy ones? When you go up and meet a new person, what's the polite thing to do? Shake hands. Do you do a chest bump? No, oh, that's stupid. That's way too personal. Getting a real up yeah, because that's too close. The first thing that interacts is the extremity on the far end. That's what interacts. So to a first approximation, that's what's creating the bond. Is that a perfect thing? Do you think you would treat your spouse, potential future spouse, boyfriend, girlfriend, whatever, only with handshakes?
We'll see.
Fair point. More than likely, you get a little bit more personable. Okay? As we start to look at those deeper interactions, we find that that theory doesn't hold, and we have to dig deeper. Do you want to dig deeper? Do you want to keep chemistry at arm's length, or do you really want to embrace it? It's just like, I don't really want to answer that because you're a chemist and you're going to make fun of me if I say I want to keep it at arm's length. Yeah.
We haven't learned a single thing in this class.
So, a couple things. Awesome question about looking at what's going on with our transition metals. Absolutely, heck yeah, it doesn't apply. Okay, why does it not apply? The whole process of the chemical bond concept in Lewis theory was designed effectively by an organic chemist. When an organic chemist looks at the periodic table, they go blind, very selectively blind, and they look at hydrogen, boron, carbon, nitrogen, oxygen, fluorine, and the halogens. The whole periodic table of 110, 18 things drops to about 10 elements, and we're only concerned about how those things interact. Why are we only concerned about those things? Those elements are the ones that dictate the vast majority of what people are studying. You're going into nursing. That's biology rooted. Guess what elements predominate the interactions that we find within that field? Those 10 elements. Do the other ones also show up? Yes, they're confusing. So organic chemists decide, I don't want to worry about it. I'll let somebody else deal with that. Okay? Is it critical to functioning through it? No. Depending on what level of chemistry you need to get to, you may decide to look at those, you may decide not to. Okay? So yes, you're right. When looking at the valence electrons within the transition elements, predicting those is more challenging to deal with. It is typically outside the scope of a Chem 130 class. So you don't have to stress about it. Okay? When we look at how we're using our valence electrons, how are we using the valence electrons? Chemical bonding. And when we look at our chemical bonds, the only things that we're really truly using Lewis theory for to figure out chemical bonding is the non-metals. Which means all those transition metals I don't have to worry about. Okay? They all just kind of fade to nothingness. We can use Lewis theory to build into those. Okay? That's the interesting thing behind it, is we can do that. Things go sideways and get really twisted and gnarly for us, so we tend to ignore that for Chem 130 and say, we'll leave that for the Chem 151 people, who then also typically ignore it. Then OChem doesn't look at it at all. And then if you need even more chemistry, that's when you'd encounter like an inorganic chemistry class where they would dig into it. How many people want to be chemistry majors? Do we need to worry about it? No. Right? So it's phenomenal to ask those questions. Just realize you will encounter things that will be way outside the scope of what you need to function within the class. You have to have selective vision. Kind of, sort of? Okay, so we've got protons, neutrons, electrons that build our atoms. We said the electrons are the most important thing. We said the outermost electrons are the most important thing, which then means we call them valence electrons. Why? Because we want a fancier name. There's valence electrons. Okay? Those now need to get involved in bonds. Okay, well, how do we know what's going on with that? Well, ultimately, there's a couple sets of rules. Did I just break it? No? Okay. Let's see what happens. Oh, because I can't. It's a scrolly. Okay. One of the primary rules that comes out is this thing known as the octet rule. Okay. We talked about already saying the only things we really cared about: boron, carbon, nitrogen, oxygen, fluorine, right? Okay. And we ignored all the transition metals. We can deal with all these other ones too. Okay, believe it or not, we can. Okay, but we don't have to. Our primary focus is right up here. What energy level is in that primary focus?
2.
The second energy level. How many columns are in the second energy level?
6.
You said 8, everybody else says 6. Why are you saying 8? Oh, come on. You added 2. Why did you add 2?
Because technically it includes lithium and beryllium.
Second energy level, 1, 2, 3, 4, 5, 6, 7, 8. Okay? We're talking about our energy levels for forming bonds. It's that outermost energy level, and it is typically going to involve that whole kit and caboodle, not just the p orbitals, but also the s. 8 was a phenomenal answer. Okay? That's what we're looking at. Okay? What's a fancy way to say 8?
Octets.
Octet. Okay? So we encounter this octet rule. Okay, the octet rule is coming about because we said if I'm looking at those energy levels, if I ignore my d orbitals, so again, that selective vision, if I could delete it, deleted, how many columns would we have? 8. Okay, and that 8 would get us out to here. Right? What are those? They're elements, Mike. Okay, yeah, they're elements. Keep going. Halogens. Awesome guess. That's these. Dang. You were just one off. What are those called? And again, remember, fair game. I don't know. Noble gases. Yes, noble gases. What do we know about the noble gases? Why do we call them noble?
They have a full outer shell.
Why does that matter? Why does that make them noble?
Because that completes the octet.
That completes their octet. When we're looking at our rules here in our octets, when we're creating bonds, what we're trying to do is make all of these elements that are not noble gases look like noble gases. That's the goal. Okay? Think about how you live. You buy fancy stuff. Why do you buy fancy stuff? So everybody thinks you have more money than you do. So that you look like the nobility. Okay? And if we don't have the money to do that, everybody makes fun of us, and that's not cool. Okay? Chemistry is effectively doing the same thing. How do we build that out to look like the noble gases? Okay? This is why it's important to know our valence electrons. Fluorine has how many valence?
7.
7. How many does noble gas have? 8. What does fluorine want to do?
It wants to steal one from somebody
It
else.
wants to steal an electron from somewhere else. What's that somewhere else? Another atom that it is bonded to, and I can now explain the bonding patterns behind that. So if I have that context, I can build that out to explain what's going on. It becomes so important that we call it the octet rule. There are absolutely exceptions to the octet rule. Most of those exceptions do not appear in a Chem 130 class, so you don't need to worry about it. Okay? So, we can continue building out our octet rule. Okay, ultimately, it's a bunch of different kind of rules. Ugh. Forgot to start recording again. Oh well. Do you know what HCl is? General experience, life experience. Again, no is perfectly acceptable. Anybody know anything about HCl?
Sounds like hydrogen and chlorine.
Hydrogen and chlorine, yes, I agree. Really, nobody's heard of HCl? Nobody has a pool? I don't have a pool either, but... Oh, okay. It's usually referred to as hydrochloric acid, right? What happens if we do NaCl? Have you heard of NaCl? Table salt. Okay. If I said hydrochloric acid versus table salt, is your visceral response different between those two things? Yeah. Why is it different? I like it. It's a good response.
Different elements going into it.
They do have different elements going into it. That's why you're like, oh yeah, I have a visceral response to HCl versus NaCl because it's sodium versus hydrogen.
No, I was gonna say one you can eat it and one you die.
HCl is death. Sodium chloride, I like eat that all the time. That's not death. Okay? Why such a drastic difference? That's chlorine, chlorine. It's the exact same thing. It's hydrogen, sodium. Freaking hydrogen and sodium. Same column. Why so different in reactivity? The bond type between them is what's dictating that difference. And if we know how to identify that bond type or classify that bond type, we can do something about predicting both how that molecule looks and we can predict something about its reactivity. We can name it differently, which is the next unit, so that we can then quickly call attention. When I say hydrochloric acid, I go, ooh, acid. Don't do that. Sodium chloride, you're like, okay. I don't know. You're like, well, I know sodium chloride is table salt. I could pick something else, zinc chloride. I don't know what the hell that is. But it's not hydrochloric acid. Okay? That acid terminology brings in a level of safety, so we want a naming system that allows for that. That naming system is coming back to the reactivity difference. That reactivity difference we can predict when we look at the types of bonds. So that when we talk about Lewis structure, our primary focus is our covalent bonds. So how do we know we have an ionic bond versus a covalent bond? Well, first we just have to define them. Sodium is classified as a metal. How do you know it's classified as a metal? Zinc does not have IUM. Is zinc a metal? Yes, it is. Damn. So IUM, not a bad idea. Beryllium, magnesium, but zinc is also a metal, so it doesn't work. How do we know sodium is a metal? Said another way, and zinc is a metal, and gallium is a metal.
The row that it's in.
Bromine, same row, not a metal.
It's like that staircase.
There's a staircase. That staircase is one of those patterns within our periodic table. If we're to the right of that staircase, we're looking at nonmetals. If we're to the left of that staircase, we're looking at
Metals.
metals, with a weird floating exception, right? That weird floating exception being metallide sitting on that line. Mercury is still a metal. Hydrogen is a nonmetal. Hydrogen and helium, if we think through their classifications, hydrogen was S, we're okay with that. Helium was also what configuration? It was also S, but isn't it in the P block? That first energy level is typically drawn off of the periodic table because it doesn't quite fit the patterns for anything. Right? So hydrogen is technically a nonmetal. But if we look at that staircase, that can help us figure this out. If we have a metal and a nonmetal, boom, ionic bond. Nonmetals, covalent bond. Okay? I can get in trouble for this, but not really, but okay, I'm going to make the argument that the whole process of bonding or chapter of bonding, our primary focus is on covalent bonds. The big lesson out of it is Lewis structure or Lewis theory, and that's based on covalent bonds. You can make hand-wavy approximations that work to describe what's going on in ionic bonding, but it's a bad idea. Okay? So, we want to be able to find our types of bonds. Dude, I got a lecture for 3 hours.
You're doing great.
You guys sit through that?
Unfortunately. She gives us like a break in between the lecture and then a
Okay.
break after.
You guys gonna let me know when you want to break?
Yes, usually 20 minutes.
Every 20 minutes?
No, it's average, usually 20 minutes.
Holy.
Get like an 8-minute
Let's put it this way. If you don't ask for a break, I will not remember, and I will talk until you are all asleep. Way into the night.
Can we pop the door open? We usually do because it's really cold in here.
No. Okay. That door should never be propped open. When it is propped open, it destroys the air conditioning system in the entire building, and the rest of the building gets really hot. Like the building is like, oh, it's cold in this room, so we're going to turn on the heat, so the rest of the building actually gets the heat. So yeah, last week when you guys had that door propped open, you pissed off everybody else in the building. Sorry. It is cold. You're wearing a sweater. That's ultimately the best suggestion I can give you. There's some aprons. There's a rainbow jacket. Okay. So ionic bonds are formed between positive cations and negatively charged anions. Okay. So this is a transfer of electrons has already happened. Okay. That's now an ionic bond. This generates a whole bunch of secondary interactions that will usually get discussed in much greater detail much later in the semester. Okay? We'll see if it pops in here because I disagree with how the textbook organizes it and they start to talk about things in gray spaces. Okay? But if we go through and look at our ionic bonds, we can reference the sodium and the chlorine. Chlorine as a negative, we're like, great, that looks like an octet, it's still charged. Charge is bad. We want to neutralize charge. So what do we put near it? More positive sodiums. So if you look around all of those chlorines, you've got positives. You can equate this to the north and south end of a magnet, right, to kind of stack those things out. If we call sodium chloride a molecule, which is bad because it's not a molecule, it's an ionic compound, and we call the next one a molecule, we get an attraction between them, and that attraction we call an electrostatic attraction. Okay? That's not a bond. I know we're in the bond chapter. That's not a bond, that's an electrostatic attraction, and if we can walk that path, but that's a distraction, I think, from the point of this chapter. Okay? Oops. Okay. So our ionic compounds, we've got these regular repeating crystal lattice. Okay? When we looked through, this is a nice kind of pictogram for it. If we look through at our formula system, that's what we had on the other side. Okay? And if I wanted to say what is the formula for sodium chloride, that becomes really challenging because I can't reach in and grab a molecule of sodium chloride. I can't. Because they aren't really properly linked, which then means when we report sodium chloride, okay, or write out its formula, which again we'll see a little bit later, we would write it in the reduced ratio. When I talk about sodium chloride, it's one sodium with one chlorine. That's not one atom necessarily. That could be thousands of atoms. But I have thousands of atoms of sodium. I have an equal amount of chlorines. That's what this formula is telling me. Kind of, sort of? Okay. And that's dealing now with our ionic bonds. We get this nice repeating structure. And as we're going through this, starting to remember some of the stuff that shows up in these slides. Okay. Cations are formed. Our cations are our positive. They're the ones that have now lost their electrons. Okay. We need to know that so that when I see sodium ion, I need to know that that is called a cation because I will now refer to that. What does that mean? You need to know that cations are positive. Cats are always positive. You had already heard that because you already started to laugh. Okay? As long as you associate those terms, you should be okay with that. Okay? So our cations are positive. We need to make sure that we've got that connection. Okay? We'll hear this word isoelectronic. Okay? Why is sodium as a metal positive? Why did it give up its electron?
To become those
The octet rule.
Part of the octet rule to look like the what?
neon.
Not the halogens, but the
noble gases.
noble gases. Okay? Because you were having the same problem. Okay? Yeah, it's to look like the noble gases. Why didn't sodium look like argon? Because argon's a noble gas.
Because neon is closer.
Really? You're going to tell me the distance between sodium and argon is further than to neon? My arm didn't even reach to neon. What are you talking about it being closer?
It's technically right in front of it.
If we take our periodic table and we kind of acknowledge that we could roll it, sodium at 11 is very close to 10 as neon. It is quite far from argon. Okay? Our metals are trying to look like the noble gases. Okay? And the easiest way for them to do that is generally to lose one electron. Except for calcium. Right? Calcium doesn't lose one electron because when it loses one electron, what does it look like?
Potassium.
Potassium. It doesn't want to look like potassium. What does it want to look like? Yeah, it looks like the other side. So what does it need to do?
Give.
Okay? Add and give is a little bit weird, and neither of them are going to be appropriate. If we add an electron, what happens? Then does it look like? It gains one, it looks like scandium. So flip. What did it want to look like?
You need to lose 2 electrons.
Ah.
Argon.
We just talked about gaining and losing. We didn't quantify there's an amount that it could gain and lose. Calcium doesn't lose one electron, it loses 2. Because it loses 2 electrons, what happens? Well, calcium, because it's defined by its protons, calcium, where'd it go? 20, has 20 positively charged things. If it was neutral, it had 20 negatively charged things. The total would be 0 as our charge. But if it loses 2 electrons, how many electrons does it have?
18.
18. Now what happens when I do that math?
Yeah.
I would have 2 positively charged structures left over. So calcium becomes a +2. So this isn't just gain and loss. I have to quantify the amount. That first column is always going to lose 1 electron rather than gaining 7. That second column is going to
Lose 2.
lose 2 electrons rather than
Gaining 6.
gaining, and we go up here, it's a little bit cleaner, gaining 6.
Lose 3.
Aluminum can lose 3, look like neon, 13 to 10, or it could gain 5. Which do you think is easier, losing 3 or gaining 5?
Losing 3.
Losing 3. What happens for aluminum? +3.
Plus 3.
Ooh, this is kind of fun. Okay, let's look at carbon.
Well, it could go both ways.
Right in the middle. It could lose, try again,
4.
4 or
Gain 4.
gain 4. Which does it do? Yes. Carbon does both. And everything in between, believe it or not. Okay? Which means we tend to ignore it. If it's in an ionic compound, we know it's being bonded with a metal, and it would typically take a -4. So you might see a table maybe later on in this where it's saying it's a -4. It's a bit questionable to call it that.
Is there like a simpler way to explain why it does that?
Which is easier for you, gain or lose the exact
No,
same
so,
amount?
Like why? Does
So-
it look like a noble gas?
The why there is ultimately shifting from what its identity. Here, what was the identity?
1.
Here,
It's on the staircase.
it's not a gas,
It's a non-metal.
it's to the nonmetal. And as soon as we transition to the nonmetal, that's where things can get a little bit of gray area, okay? And ultimately that gray area is coming back to deciding, is it making a covalent bond or an ionic bond, okay?
And that goes the same for the metals too.
And in the metals, what happens when a metal bonds with a metal? That's a really good question. What kind of bond do you think that is?
Ionic.
An ionic bond is defined as metal and nonmetal. So it ain't ionic. Covalent. Covalent is nonmetal and nonmetal. So what the hell is metal and metal? Outside the scope of the course. You don't need to worry about it. It's called a metallic bond. Okay? And different things come into play there. Right? So what happens with our nonmetals is that when we look at bonds with our nonmetals, they can be both ionic and covalent. When we look at our metals, they can only be ionic, which means they hold a charge, a static charge, pretty well.
Oh, so
The nonmetals now run into this gray area. Are we looking at it as an ionic compound, or are we looking at it as a covalent compound?
So it's to be stable.
It has to do with stability. It has to do with a bunch of other things that we could look at when we look at Lewis theory a little bit. Okay. Nitrogen. Why gain 3?
Because it's easier to gain 3 than
Look at
lose
the
5.
opposite. It's gain 3 to look like neon, or lose 5 to look like helium, which is easier. Now gaining or losing. Now it's easier to gain. Do you need to know all of that and have all of that memorized?
Yeah.
Isn't a bad statement. Okay? You should push for a periodic table allowed on your exam, and what I would argue you do as soon as you get the periodic table is you write down at the top of the column +1, +2, -3, -2, -1. Now you know. Ta-da! You don't have to have it memorized anymore. You can just put it up there. Kind of, sort of? Okay. So our isoelectronic looking like our noble gases. That's kind of the point. Okay? So if we look at our cations, we're typically talking about just losing 1, 2, or potentially 3 electrons. You'll note that when we talk through, I think there's a chart a little bit later that I'll complain about. We talked about the group 1, the group 2. Everybody remember that? We talked about the group 1 plus 1. We talked about the group 2 plus 2. We ignored all hell in there. We looked at the aluminum and we said plus 3. Okay? You can't officially ignore everything in here. Okay? It is going to come back to haunt you a little bit. You will eventually, probably, and each instructor is different. I definitely make students do it. Memorize, that's not legible at all. Those 2 are plus 2, and that 1 is plus 1. Okay? This establishes our cations. The one that I said was plus 1. Thank you for looking at the periodic table. That's awesome. Which element is that?
It's gold or silver, I don't know. I know they have that here.
The one that I said was plus 1.
Silver.
Okay? If we look at my pattern on here, there's our aluminum. We're going down 2 from aluminum, and we're going across to silver. Silver is a plus 1. Cadmium and zinc are both plus 2. That's what's written there. If they're in the same family, what's their reactivity? That's now chapter 5. Same family, not positive. What does it mean if you're in the same family? You react the same. So if I establish that silver is a plus 1, cadmium is a plus 2, zinc's also going to be a plus 2. Okay. The problem with that is that we don't want to memorize copper as a plus 1. Okay. Why not? Because it has a bunch of charges. Why does it have a bunch of charges? Where is it?
In the metal.
It's in the, not just the metals, it's in the transition metals. The transition metals become challenging because we're now looking at d orbitals, and our whole octet Lewis structure philosophy does not apply well to the d orbitals. Okay? So things go sideways real quickly in there. Okay? Yes?
Is there any known charge for tin and lead?
Yes. So all of our elements except the ones in white will have known charges. Okay? The question becomes, is it a single known charge or are they multiple? Okay? There's a reason I didn't point those out, because they could be multiple. Okay? They could be because I honestly don't know, but I think they do have multiple charges. Okay? And we want to avoid dealing with those because those are now so low in the periodic table, okay, that as far as I'm concerned, what are the odds you're going to deal with those? You won't. Our primary focus for Chem 130 is keeping it relatively simple and not dealing with the challenging things down below. Okay? The anions flipped the system because they're now closer to the noble gases on the other side of the noble gases, if you will, so they end up gaining electrons. We again encounter this term of isoelectronic. It's the same electrons. Why didn't we make it same protons? Why doesn't chlorine try to gain a proton to look like argon? Why doesn't fluorine try and gain a proton to look like neon? What happens to the identity of fluorine if it gained a proton? It turns into neon. Okay? So we lose the identity of the element. The only thing that we can change without changing the identity of the element is the number of electrons. That's why we're talking about isoelectronic and not isoprotonic. Okay? Because that's now changing the identity of what we're referencing. Okay? So our formation, let's see, they probably go through and talk about the different charges. We can look at equations. We can look at electron configurations. And again, ultimately, all of that is a deeper, more involved explanation than just acknowledging where they are on the periodic table. Depending how comfortable you are, like some people wanted to look at electron configuration, for heaven forbid, okay? We could just memorize those patterns so that we don't have to worry about the electron configurations. Okay? Next part. Yeah, I'm remembering these slides. Okay, ionic radii. Okay, chapter 5. I know we've already expressed that we are struggling to remember some stuff. That's okay. In chapter 5, theoretically, yeah, I think it was chapter 5, you talked about learning something about the radius of your elements, or the radius of an atom. Okay? Theoretically, I don't know if you've been tested on that or not, but you're supposed to memorize certain pieces about radii. Okay? Well, what dictates radius?
It's an orbit.
Diameter? What do you mean orbit? What orbit? What thing is orbiting?
Electrons.
Electrons. When we're talking about the size of an atom, we're talking about its radius. And the radius is, again, the electrons on the outside. Okay, so when we're talking about ionic radii, it's all based on where the electrons are located. So if we were to look at our periodic table and just talk about neutral atoms, say sodium, and I wanted to compare that to, say, lithium, I could make an argument about what happened to the size of the atom. And we're saying size, we're saying radius. What happens as I go from lithium to sodium?
It increases.
It gets bigger. Why?
Has more electrons.
More electrons. Perfectly decent observation. It has more electrons, it therefore gets bigger.
Has a larger mass.
The mass is a different statement. Okay? And you're right, it does have a larger mass, but that's not why it's getting bigger. Okay? Because where's the mass held? What subatomic particles hold mass? The nucleus is not a subatomic particle, but the particles in the nucleus hold our mass, which are protons and neutrons. Why are we not referencing the protons and neutrons when we look at size? Size, we're referencing the volume of the atom,
Which is the electron.
which is the electron. Why is it not the protons and neutrons?
Because
They're
they're
all
in the middle.
held in that tiny little space, okay, in our nucleus. Okay, so it's the electrons that are largely dictating our size, okay, and largely becomes an operative word. So, your awesome analogy here, lithium to sodium, it gets bigger because more electrons. Everybody cool with that? We don't want to be cool with that, but we'll see. We don't know why yet. Lithium to beryllium, what happens to the amount of electrons?
It's smaller.
I didn't ask about the size of the atom, I asked about the number of electrons. As I move from lithium to beryllium, what happens to the number of electrons?
Goes up. By one.
It goes up. It increases by 1 electron. Okay? So you said lithium to sodium, bigger because more electrons. Lithium to beryllium has more electrons, which means it should be bigger. And yet,
It's not.
it's smaller. Well, it's an exception. It's not an exception, and I don't mean this as an insult. It was a trash explanation to say it was more electrons, because that's not why it's getting bigger. Where are our electrons going when we go from lithium to sodium?
The outer.
Yes, the outer. Describe more the outer.
The energy level.
Ah, there it is. It's the energy level. When we go from lithium to sodium, we've put our electrons in a higher energy level. Ta-da, that's why it got bigger. It's not that there's more, they're going to a higher energy level. What's happening when I go from lithium to beryllium? Beryllium adds an extra electron.
The energy level stays the same.
The energy level stays the same. How do I know it stays the same?
Because it's still in the second.
It's in the same row. Cool. So what does that mean happens to size? And this might be the thing.
How much does it, how does it get smaller?
Okay, let's cross that bridge in a second. What would we say happens to the size if the electrons go to the same energy level?
It stays the same.
It stays the same. Shouldn't change. Okay? As we go down, higher energy level, it gets bigger. As we go left to right, same energy level, so it should stay the same.
So
It doesn't.
atoms only differ in size.
Well, I didn't finish because she's right. And other people were saying the same thing. The size does, big old air quotes, because I'm an organic chemist, does change a little bit left to right. Okay? So you're right. It does get small. Why does it get smaller? The electrons are going to the exact same energy level. Is that the only thing that changes? As we go left to right, it's the volume actually decreases. Why does it get... We're adding an electron. I added electrons here and it got bigger. I added an electron here, it gets smaller. What else is changing as I go from lithium to beryllium? You want a really stupid change? Can I put a stupid change out there? Yeah. The L becomes a B. The I becomes an E. What else is changing as we go from Li to B?
The actual atom itself.
What defines the identity of the element?
Like it goes like the metals and then the gases.
These are still both metals, and the trend is still that this is smaller than that. Nice idea. I like you're fishing for those theories. That's awesome. What else changes as I go from lithium to beryllium? Because right now, if I were to look at my lithium, there's my outer electron, there's beryllium, outer electron, we'd be saying same energy level. I'm representing the arrows as electrons. They should be the same energy level, they should be the same size. What else changes as I go from Li to Be?
You're changing groups,
Nope, same group. It's not officially the same group.
or you're gonna get.
Not a bad idea, but no. Try again. What else changes? I like where you're thinking, not quite right though. What contributes to atomic mass? The number of protons and neutrons. Are the neutrons going to do anything to our electrons? No. Why? It's neutral and negative. Like there's no reason for them to interact. That's why I don't like atomic mass, because neutrons aren't doing anything. What's the other part of atomic mass? The protons. And what's special about our protons? They're positively charged. And what's attracted to a positive charge? A negative charge. So as I go left to right, at a first approximation, they stay the same. But, awesome observation, beryllium has an extra proton, which means that beryllium is slightly more positive. What does it do to those electrons? It brings them in just a little bit closer. This is why when we move left to right, the size gets smaller. Because what do is we continue to move left to right. We're continually adding more and more protons. Those more and more protons suck in those electrons. But dude, didn't this one have more protons? It got bigger. Why did it get bigger?
It also got more electrons.
Energy level.
Where the electrons are located. The energy level is a much larger effect than the size of our nucleus. Okay? Kind of makes sense? Cool. So we recover chapter 5 and we feel better? Cool. Okay. Ionic. What does it mean when we're ionic? What are we doing? Ionic isn't necessarily sharing. In fact, it's the opposite of sharing. What does it mean to become ionic? If I looked at lithium and I made it ionic, what happens to lithium?
You lose an electron.
Boom, that electron goes away. Doot. Of course, I erased everything. Right? No longer there. Did lithium only have one electron? It had 3. We had a lower energy level electron state down here, right? We removed that 1. Now when I look at the size, I'm not referencing that 1 electron anymore. What do I have to reference as the size? The highest energy level electrons, which is lower energy level. What happens to the size? Did it get bigger, or did the electrons get pulled closer? They're closer, which means what happens to the size? It gets smaller. What happens to the sodium atom when it loses an electron? Okay, it gets smaller. Okay? We've removed that outer energy electron. We're now at lower energy electrons, which by definition means we're smaller. We've shifted the energy level. What happens for chlorine?
It gets bigger.
You're going to ruin all the punchlines, aren't you? It's okay, no one heard you, right? Fluorine, we had our 1s, we have our 2s, we have the 2p. 1, 2, 3, 4, 5, 6, 7. A bunch of electrons for our fluorine. What happens to the fluorine? We add yet another electron in there. Okay? Same energy level, what should happen to it? Same energy level, what should happen to it?
Oh, she gets smaller.
States.
It stays the same. Same energy level, it should stay the same. Okay? Except what was holding it in was the size of the nucleus. We now have an excess of electrons. Can the nucleus hold this tighter? Nope. So what happens? Now it expands a little bit. Does that make sense?
Yeah.
So you're right. The end conclusion is that when we add that extra electron, it gets bigger. Okay? It's still going to the same energy level, but the nucleus now hasn't also grown to hold it in tighter. Kind of, sort of? So when we're talking about our ionic radii, what we're now saying is that a cation gets smaller than its neutral atom, and the anion gets larger than the neutral atom. That's all they want you to do. Kind of, sort of? Okay? And you can quantify the junk out of it if you really wanted to. I don't really want to, and I doubt your instructor is going to have you try and calculate all sorts of numbers or memorize numbers on that also. Okay? What happens when we move to a covalent bond, though? Okay, the ionic bond transferred electrons. Whoop, there you go. Have all the electrons. In a covalent bond, are you transferring electrons? No, you're sharing the electrons. So what should happen to the radius of the atom? Is it gaining an electron? No. Is it losing an electron? No. So what should happen to the radius of the atom? It stays the same. Okay? And you're right, it does. Okay? So what do we end up discussing then if we're talking about the individual radii staying the same? Okay, well, we can't now reference an individual radius because it's a covalent bond. It's no longer atom 1 and atom 2. It's these atoms have come together to form a new thing. So defining the radius is now kind of bizarre. I can't name it for the pieces, but what I can try and think about is what happened with those pieces. If I look at the individual atoms and I now make a bond between them, that bond means this one's electrons are sharing with this one's electrons, and vice versa. Okay? So if I just brought them close enough to each other, call that one the white one, and this one, or that was supposed to be a bigger green circle. Whoop. Okay? We could now reference the bond length, the distance between those radii.
Can't see.
Ow. Okay? And that's cool. We could reference that. Why do we reference that? Well, if we were putting them together, we might say, well, they're spheres. They come next to each other, and ta-da, we have a bond. Except what we notice is that the bond length, the nucleus to nucleus distance, isn't the sum of the radii. Okay? Well, what made the radii? What dictates the size of our atom? What dictates the radius of the atom? You're getting circular. You need to go somewhere else. The electrons. If we are sharing electrons between atoms, this circle here needs to overlap with this circle here. So the electrons are now being shared in between both spaces, which means what happens to our bond length? It's smaller than the sum of the radii. That was a stupid fancy way of saying we're just sharing electrons. Okay? But that's what they're referencing here. So if we look at the HCl, we look at a hydrogen atom and a chlorine atom, we can look at their radii, we can quantify those numbers. If we added those two numbers up, we get 136. If we look at the actual center to center distance, It's 127. Why? Because those orbitals have to overlap to have sharing electrons between both atoms. Kind of makes sense? Cool. My recording says 60 minutes. This is going to be a long, long recording. Do you want to break at 60 minutes? Or should I just keep digging? Like I said, I will keep shoveling stuff at you until you tell me to stop.
I'm going to keep going.
Move on, we do. Bond energy. I don't want to talk about bond energy. We can quantify and look at the energy associated with a bond, is ultimately what this is saying. Okay, you can look at the individual atoms on their own, okay, and then you can look at the atoms or the energy that's formed when you make the bond between them. Because if we think through how a chemical reaction is happening, we have individual atoms floating around, chilling on their own. And then we also have them connected to each other. Which one should be a lower energy state? Which one is more stable? Them chilling on their own or forming a bond?
Forming a bond.
Why is forming a bond lower in energy, you think? It's a hard question.
If they're chilling on their own, does that mean that they have to find a way to stabilize themselves?
So why is it more stable to have them bond up? It's a pretty deep philosophical question, to be honest. Okay? Do we know for a fact the bond should be lower in energy?
Yes.
Yes. Okay? So now it's a question. We know that. Why do we know that? Why does it make sense that we have bonds and not just atoms?
Is it because they can share neutrons?
We exist. Are you a single atom? No. You're a collection of atoms that have formed bonds. If our atoms were more stable as atoms, would we ever come together to make bonds? No. We're a lower energy state because we have made bonds. That's it. Right? And we can quantify that. You can look at quantum mechanics and all sorts of crazy stuff like that if you really want to. No one said they wanted to become a chemist, so you don't care. Realize that when we make a bond, we're going to release energy. That's the big deal. If you're going to break that bond, it takes energy to break it. Okay? If I want to pull atoms away from each other, I have to add energy in to break them apart. That's the key lesson that you need to pick up with.
Wait, so when you form a bond, you lose energy?
You will release energy. Okay? So if we're looking at the chemical reactions, okay, in this top one, we're forming a bond. Right? Because we have H plus Cl, those are separate things. We have HCl, they're now connected. What happened? We see heat over here as a product on our reaction arrow. Okay? That product means that this is referred to as an exothermic. Have you heard of therm before? Okay? Theoretically, you should all learn about therm because it'll help you not be cold in here. You could go buy some thermal underwear whenever you come to class. Okay? The whole point of thermal is referencing temperature. What is exo? Out. An exoskeleton. It's a skeleton on the outside. Bugs. Okay? So when we're talking about this reaction, we're saying outside energy. The energy leaves. It's a product. Here, what's happening? The energy is being put in as a reactant. So this one I would call endo. Like an endoskeleton. So we get endothermic. Okay? Kind of, sort of? Cool. Okay, we're going to exit the drawing. I'm going to pause the video because this is going to show something I'm not going to like. What we now say is that we've got these general philosophies behind everything. How can we make some compounds? Let's take some atoms and we actually put them together. How do we explain where those electrons are going? How do we arrange them? This is ultimately Lewis theory. So what we're talking about, there it is. Here, I'm going to pause it right here.